VantTec is a group of students from Tec de Monterrey, focused on the research and development of autonomous unmanned vehicles. The team emerged in 2017 as a multidisciplinary project with undergrad and graduate students that were interested in state-of-the-art technology research. The first objective? To participate in the 2017 RoboSub competition. Afterwards, the team evolved, and under new leadership, 3 objectives were defined. Win RoboBoat, inspire new generations of students, and expand into new competitions. This year, we accomplished them all by participating for the first time in RoboSub 2020.
Hi, my name is Pedro Sanchez. I am the team lead for the VantTec RoboSub 2020 team, as well as the head of the software development, tasked with the design of the overall system architecture, as well as the software architecture involving ROS and FreeRTOS. I was in charge of the system identification, modeling, and simulation, as well as the development of the control and guidance algorithms. Finally, I supported the mechanical, electrical, and electronic aspects of the design and development of the submarine, as well as the mission solution design and implementation.
Hello, my name is Melissa Sanchez. My work consisted on project planning and management support, as well as supervise the whole mechanical design, the 3D model development, and the selection of materials in order to achieve a reliable and efficient vehicle.
My name is Ivana Collada. I'm head of perception development, including data augmentation and object detector training. I also help in the overall planning of the missions for the different challenges and the overall project management, including CAD design and prototyping.
My name is Alejandra Monsivais, and my role was to project manage part of RoboSub 2020 competition, as well as the power electronic circuit design development, where ECU actuators and sensors integration, and PCB design assembly, as well as prototyping.
Hi, my name is Alejandro Gonzalez. I am the president of VantTec. My work with RoboSub has been to provide continuous support to the project planning and project management apps of the team, as well as technical support in the development of the guidance, navigation, and control system, including assistance in the strategies to solve the attempted tasks.
Hi, I'm Christina. I'm an industrial designer. I was in the manufacturing team. I helped redesign last year's submarine model to help design 3D models for some components.
Hi, my name is Gabriel Leal, and I was in charge of the design of the frame for the submarine.
My name is Diego Martinez. I worked in the mechanical design and manufacturing. I helped with the arm and gripper system designs and the 3D modeling.
Hi, my name is Pedro Ortega and I collaborate in the mechanic system department.
Hello, my name is Pedro Games. I am the head in electronics department, in charge of the power electronics circuit design, the actuators and sensor integration circuit, as well as the printed circuit board design and assembly, while also providing support on manufacturing.
Hi, my name is Gerardo Berni, and I am part of the software development team. I work in the perception simulation development as well as mission solution design. I also gave support on ROS architecture development.
Hi, my name is Andres Sanchez. I'm part of the software team, where I worked on the design of solutions for the UAV missions, and I also gave support on ROS architecture development.
Hi, my name is Edis, and I work in the UAV software team. My job is giving support on ROS architecture development by simulating the mission solutions for the challenges we chose to tackle.
My name is Penelope and I worked in perception development, helping with data augmentation for object detector training.
Hi, my name is Sebastian Martinez and I'm part of the perception development team. And for the RoboSub 2020 competition, I help in the data augmentation tasks to enlarge our dataset and into training the multi-class object detector.
Hi, my name is Roberto Mendivil. I am part of the perception team. I work on a multi-class object detector for the obstacles, and I also supported the electronic system design for the UUV.
Hello, my name is Rogelio Sandais, and I'm part of object detector training. And I help create a MATLAB script that label hundreds of data augmented images to later use to train our detector that we were going to use in the submarine.
Hi, my name is Nadia Garcia, and I'm the head of media development for VantTec. I also helped in the perception team by creating the first dataset by editing previous datasets with the RoboSub 2020 team.
Hello, my name is Jorge Cosmetin, and I work in the embedded system.
Hi, my name is Ernesto Monroy, and I collaborate in embedded systems department.
VantTec U3 unmanned underwater vehicle mechanical design is based on robustness, modularity, and ease of manufacturing.
The frame consists of structural pieces that support 3 acrylic electronic enclosures, and additional systems such as the torpedo launcher, the marker dropper, and the gripper. The frame also has the function of protecting the thrusters in case of collision and of dealing with the static and dynamic loads. Aluminum 6061 is used for the exterior frame of the vehicle, as well as for the inner lateral supports. In the case of the central supports, ABS filament is used due to the complex shape and durability ABS provides.
The enclosures house the electronic boards, the sensors, and the batteries. The main enclosure contains the PCB boards, sensors, and processors. Both of the secondary enclosures are 3-inch diameter cylinders, each holding an independent battery. The enclosures have silicone sealant to avoid leaks, as well as plugs in the end caps, either to route cables safely or seal the in-use holes. For the actuators area, we have a 6-thruster configuration to actuate the system using Blue Robotics T200 thrusters. The torpedo launcher is composed by 2 linear actuators and a torpedo container. The gripper consists of 2 servos, one for extension and the other for gripper actuation. And the marker dropper is divided in 3 parts: a container, a sliding platform, and a linear actuator.
The electrical and electronics design was driven by 4 main constraints. The requirements stemming from challenges from previous competitions, the need for a deterministic firmware behavior and accurate data acquisition, high computing power for algorithm execution, and component reliability and safety. To tackle these requirements, a decentralized architecture was devised, distributing tasks between an electronic control unit and a central processing unit. The electronic control unit is an STM32F103 microcontroller and is in control of actuator manipulation and most of the data acquisition. It runs FreeRTOS. The CPU is an NVIDIA Jetson TX2 running robot operating system tasked with the guidance, navigation, and control algorithms. Both are interconnected via a CAN bus. A VectorNav VN200 IME was chosen for the VantTec U3 to obtain velocity and position. Also, to provide an accurate way of measuring depth, a pressure sensor was added to the system. Additionally, 3 hydrophones were included since challenge locations are identified using acoustic finger signals. A Stereolab set mini stereo camera system was proposed because of its capability to both detect objects using camera images and localize them with depth perception. A Raspberry Pi camera module is also part of the architecture, providing a bottom-facing view from the vehicle perspective. For system safety, a Blue Robotics leak sensor was selected to provide an emergency signal for the internal electronics in case of seal failure. A visible, accessible mechanical kill switch is included to cut off power to all of the vehicle subsystems in case of emergency. Finally, 2 power supplies were included, one 14.8 volts for the thrusters and the other one of 11.1 volts for the rest of the components. Additional circuitry was included to provide different ranges of voltages we need, which go from 3.3 volts up until 16 volts. The software architecture design was driven by 2 main objectives: to exploit the potential of the components and peripherals available for the vehicle, and to accomplish the requirements needed to successfully solve the challenges of the competition.
For the ECU components, a communication bridge module for data transfer between the ECU and the CPU, an actuator control module, a sensor monitor module. These applications run on a real-time operating system which manages the priorities of the task and ensures determinism. Similarly, the Ubuntu 16.04 base CPU runs Robot Operating System (ROS) Kinetic, where the various software components interact between them as ROS nodes. An ECG bridge to link between the ECU and CPU, a controller module, a guidance module, a mission manager module, master node, a perception module, and an odometry module. Additionally, the ground station also runs ROS Kinetic and is connected via Ethernet to the UUV.
For path-following control capabilities, a line-of-sight guidance law was implemented alongside a nonlinear PID. This guidance law would fill the PID controller the desired heading values. In parallel, an algorithm would calculate the appropriate search speed to approach the target destination smoothly, as well as the depth references.
For the computer vision algorithms, the convolutional neural network yellow tiny tree uses the RGB image from the set camera for buoy detection. The stereo point cloud is used to calculate distance, size, and orientation of buoys and other objects. The Raspberry Pi camera is used as a down-facing camera, and its RGB image is used for detecting directional markers to different challenges. For training the CNN, images from past RoboSub competitions were edited to represent these competitions' buoys. A data augmentation library was created to reduce the number of images that had to be edited by varying elements like color, illumination, orientation, and distortion.
Based on the presented system, the VantTec U3 should be capable of solving every challenge. The autonomy capabilities of the system, such as path-following control and object and sound detection and localization, allow us to be confident on solving the gate and buoys challenge. Likewise, the torpedo launcher, the market dropper, and the robotic iron gripper allow the system to solve the torpedo, pin, and octagon challenges. The original strategy was to attempt only the gate and buoys challenges, as the objective was to build a robust and reliable software and hardware system. This objective gave a higher priority to the main system, which is the base UUV design and the autonomy capabilities. In this way, certainty exists that we can accomplish the gate and buoys challenge. Nonetheless, as COVID-19 grew, home office and simulation became our only working platform. As our manufacturing process was not possible to do, we increased time working on the challenge-oriented hardware subsystems design. Finally, the torpedo task was added to the strategy during simulation development, where we expect a 70% success ratio, which would increase once in-water testing begins.
Using the mathematical model of the UUV, the states of the vehicle could be estimated, simulating what the odometry node would do in real life. These values were then output to RVIS, where the 3D CAD model of the submarine would be used to represent the position and movements of the vehicle in space.
Software modules were developed to build the test environments for each of the challenges, simulating the job of the perception module, only publishing the objects that are inside the conical field of view. Simplified 3D models of the involved obstacles were also designed.
As a first validation of the guidance and control subsystems, a set of predefined waypoints were input to the guidance module, forcing the vehicle to follow a specific path with varying changes of heading and speed.
For the gate challenge solution, the UUV executes a search algorithm, which consists of a yaw sweep to locate any obstacles that are in range. If the obstacles are any other than the gate, it will advance to a point in front of it before starting to sweep once more. Once the gate is located, it is assumed that the computer vision algorithm successfully detects which side of the gate corresponds to which figure. 3 waypoints are then calculated, one in the front, one in the middle, and one in the back, so that the UUV crosses and passes the gate completely.
For the buoy challenge, a two-step detection and identification process was selected as the proposed approach. Using the same search algorithm from the gate challenge, the UUV searches and tracks the position of each of the buoys. Once it has already found both of them, the Euclidean distance between them is used to obtain a midpoint, around which the vehicle then orbits facing always towards the buoys in an attempt to identify them, so that it can know which one to approach according to the assigned site.
For the shorter challenge, it was assumed that there will be one board with 2 sides. The simulated challenge focused solely on aligning the vehicle to the center of the board, so that the aiming algorithm will then take over. The UUV looks for the board. Once it is located, its center point is used as a reference to create a circle with a radius of 2.5 meters around which the vehicle then orbits, looking for the desired image. Once the orientation of the image matches, the UUV stops and aligns its heading with the center.
Even though the physical development of the submarine was halted due to the COVID-19 pandemic restrictions, the team showed its resilience and adaptability by switching its development to a digital twin that enabled the simulation of the motion planning and path following algorithms, as well as the competition challenges such as gate, buoy, and shootout. Furthermore, the results of this virtual simulation environment show that the proposed solutions are technically feasible, since all of the challenges were completed successfully inside the simulation.